Welcome back to QHSE Talks. If you walk through any busy warehouse, it's easy to look at the controlled chaos and think that when an accident happens, it's just an instance of bad luck. But in safety engineering, incidents are never random. They are the direct result of uncontrolled energy interacting with people, equipment, or structures. To stop these incidents, safety engineers develop a specific analytical mindset. It's like putting on a pair of invisible glasses with a heads-up display. Suddenly, the everyday objects around you are replaced by the physical forces and mathematical variables that dictate workplace hazards. By learning to read these invisible forces, you gain the ability to accurately predict and prevent incidents before they ever happen. Let's turn those analytical glasses on. This diagram shows us that energy in mechanical systems exists in three primary measurable forms. First, we look at moving equipment to find kinetic energy. This is the energy of motion, and it determines exactly how severe an impact will be. Look at the equation. Because velocity is squared, doubling the speed of this forklift multiplies the total energy and the potential danger by 4. Next, we pan up to elevated loads. This suspended crate represents potential energy. Potential energy is a stored hazard waiting to be released by gravity. Any object at height holds this stored energy, dictated by its mass, gravity, and the total distance it could fall. Finally, we check tension systems for elastic energy. This energy is stored when materials are stretched or compressed. Pressurized hoses, springs, and cables hold immense mechanical power, making them hidden threats if that tension releases unexpectedly. Recognizing these three states of energy, kinetic, potential, and elastic, is the absolute first step in hazard recognition and risk quantification. Let's look at what happens when things go wrong. Imagine a high rack gets bumped. We'll freeze time right at the exact moment a heavy pallet of bricks tips past its center of gravity. This brings us to Newton's first law, inertia. These bricks were safely at rest. They would have stayed that way indefinitely, but an external, unsecured force acted upon them. Now we have an active struck-by hazard. To understand the danger, safety engineers use motion equations. By factoring in the initial velocity, the acceleration of gravity, and the time it takes to drop, we can map out the exact trajectory of the fall and calculate the precise stopping distance. As the bricks accelerate downward, we also have to calculate their momentum. Momentum is simply mass multiplied by velocity, and it measures the total quantity of motion. This calculation provides a real-time warning for how severe the impact will be. With every fraction of a second, a falling object accumulates massive, calculable amounts of destructive momentum. If we isolate just a single falling brick mid-air, we can break down its specific physical properties to see the real danger. This split-screen diagram highlights a critical distinction between mass and weight. Mass is the constant amount of matter inside the brick. Weight, however, is the specific downward force created by gravity pulling on that mass. This leads us to Newton's second law, where force equals mass times acceleration. The brick's constant mass, multiplied by its acceleration from gravity, results in the final destructive impact force. Calculating these distinct forces is exactly how safety teams build reliable crane load charts and perform safe rigging calculations. Weight is a dynamic, multiplying force. It dictates the absolute minimum structural requirements for any piece of safety equipment you place below a load. Down on the floor, a worker stands in the drop zone. But an engineered safety countermeasure, a reinforced catch net, deploys just in time to intercept the fall. The first line of defense here is friction. As the bricks hit the net, the overlapping materials of the safety system rub against each other, creating a frictional force that resists the downward motion and begins to slow the hazard down. Next, the net performs what physicists call work. Work represents energy transfer caused by force over a distance. As the net stretches downward, it uses force across a physical displacement distance to safely absorb all that incoming kinetic energy. Finally, Newton's third law states that every action has an equal and opposite reaction. At the moment of maximum stretch, the downward action force of the falling load is perfectly countered by the upward reaction force of the tensioned net. Effective safety equipment doesn't defy physics. It leverages work, friction, and reaction forces to safely bleed off lethal energy before it ever reaches a human being. Returning to real time, because physics were properly accounted for in the net's design, the hazard is caught safely and the worker walks away entirely unharmed. We can turn our analytical glasses off and return to a normal view of the workplace. Safety professionals don't need literal smart glasses to do their jobs. They use core mechanical equations to clearly see the forces at play and engineer out hazards on paper first. This is the ultimate purpose of understanding mechanics. It allows teams to predict hazards, accurately quantify risks, and design effective controls long before a worker ever steps foot on the site. Mastering these mechanics ensures that even when a system fails, the environment is already designed for survival. Thank you for learning with QHSE Talks. If this deep dive helped your safety practice, please like, share, and support the channel. See you in the next episode.